Hi, today we're going to talk about thermal calculations for semiconductors. It's a relatively easy topic, it's easy to calculate, and it has a lot of value in determining how much heat is dissipated and what the temperatures are in diodes, switches, transistor switches, and power transistors. And like I said, it's easy to do, and I think it's a lot of fun to know what your temperatures are in your semiconductors. You can't always tell by touching the case or touching the transistor. That's not a good way to determine how reliable the transistor is going to be and how much power you're dissipating. So we're going to get right into it, and hope you like this video. Okay, let's talk about diodes first. This is a typical diode of 1N4148. First thing you do for a thermal calculation on any semiconductor is to calculate the power dissipation. The power dissipation is the voltage times the current, which is the forward voltage drop in this case of the diode, times the maximum current. In this case, from the data sheet, the voltage drop across this particular diode is 1 volt. It may be different for an LED, it probably will be, maybe 2 or 3 volts. But from the data sheet on the 1N4148, it's a 1 volt drop, forward voltage drop, and the maximum current is 0.3 amps. If you multiply those two together, you can see the maximum power dissipated is 300 milliwatts. Now we check the data sheet. There's two kinds of checks we can do here. From the data sheet, the maximum power dissipated is 500 milliwatts at a 25°C degree ambient. And you can see that's higher than our 300 milliwatts we have in this particular case. The next thing you can do for a check is to look at the thermal resistance. Thermal resistance is denoted by the Greek letter theta, which you see here, theta JA. The resistance, thermal resistance, is theta JA, which is the junction to ambient temperature. We're most concerned about the junction. We don't care how hot the case or the plastic case or the metal case is, but how hot the junction gets. So as a result of that, we have a thermal diagram here which shows the junction, the thermal resistance, which is theta JA, and then the ambient temperature is 25. So the junction connected through a thermal resistor here, resistance to the ambient. The temperature rise in this case we said was the power dissipated, which is 0.3 watts, times 300 degrees C per watt. That's the particular thermal resistance for this 1N4148. If you multiply those two together, 0.3 watts times 300 degrees C per watt, you get a 90 degrees C rise. So the total junction temperature is the ambient plus the rise, or 25 plus 90 C, equals 115 degrees C. The maximum junction temperature listed in the data sheet is 175 C. So we're okay here. One other thing to remember is you can cheat a little bit. A lot of the temperature, or some of the temperature from the diode that's dissipated, is through the leads. So if you keep the leads short and connect them to a good thermal type of heatsink, like a terminal strip, you dissipate a little bit more power through the leads of the diode. Okay? Next we're going to talk about transistors. Okay, let's talk about a transistor now. This is a typical transistor switch configuration. A 2N2222 in a plastic TO92 case. This is the schematic, and it's a typical saturated switch which has a voltage across it here and limited by a resistor through the which limits the current through the transistor. So the first thing you do is calculate the power dissipation by looking up the VCE sat. That's the saturated voltage when the switch is turned on between collector and emitter, and you multiply that times the maximum current. In this case, I found that the VCE sat is 1 volt, that's the voltage across the transistor, times 0.6 amps. Why? Because that's the maximum current allowable to this transistor. And I came up with 0.6 watts or 600 milliwatts. Now you can also use this formula to determine what your actual current is. If you know the supply voltage, the VCE sat, and the resistor value, you can calculate the current through the resistor, which is also the current through the transistor. Okay, so now I look up at the data sheet. The maximum power dissipation allowed is 625 milliwatts at 25C, so we're okay there. Another way to do this is using a thermal resistance chart. The important thing again here is the junction temperature. This is the resistance chart diagram for the transistor with, again, R theta JA, junction to ambient. It happens to be, for this transistor, 200 degrees C per watt. If it's a different case, the thermal resistance will be different. They make this transistor also in a metal case, and the thermal resistance is a little bit different. So the temperature rise would be 0.3 watts times 200 degrees C per watt, or 60 degrees C rise. The total junction temperature then is the ambient plus the rise, or 85 C. The maximum junction temperature is, in fact, 150 degrees C. So we're all set there too. Next, we'll take a look at maximum power dissipations. Okay, here is a excerpt from a data sheet which talks about the maximum power dissipation for a 2N2222. Here it gives a couple of different values. The total device dissipation with the ambient at 25C is 625 milliwatts, as we saw before. If you're above 25C ambient, then you derate it or reduce that by 5 milliwatts per degree C. They also have a metric here, which is the total device dissipation if you keep the case at 25C, and that's 1.5 watts, more than twice the amount. But you have to keep the case at 25C somehow, and that's the problem. If you're above 25C for the case, then you derate it by 12 milliwatts per degree C. And again, the operating and storage junction temperature range in this case is 150 degrees C. Okay, next we'll take a look at a power transistor with a heatsink. Okay, here we have a power transistor with a heatsink. This happens to be a 2N3055 in a TO3 metal case. It's made to be hooked up to a heatsink. The diagram looks like this. This is typically used in a pass transistor in a power supply. And again, power dissipation is typically the voltage across the transistor times the current through it. So the voltage across it is VCE sat, if this transistor is turned on fully, times I max, and that would be 3 volts times 10 amps, or 30 watts. Now, if it's used in another mode where you don't use VCE sat because it's not turned on all the way because it's regulating, then you have to find out what that voltage is. And you can do that either analytically or by measuring it. But in this case, let's assume we have 30 watts being dissipated by this transistor. From the thermal resistance chart, we draw that, and this is the junction. And then there's several resistances here you see. One is resistance of the JC, that's junction to case. So that's from the junction to case. Here is the theta from the heatsink compound, or the sill pad, that is between the transistor and the heatsink. And then you have the thermal resistance of the heatsink itself. And I've written down what these are. It's 1.52 degrees C per watt for this transistor, for the JC. You get that off the data sheet. Heatsink compound, it's not much. I made an assumption here about 1. And the heatsink I'm going to use is 2 degrees C per watt. So what you do here to find the total thermal resistance is you add up all those thermal resistances, you can come out with 4.52 degrees C per watt. The total rise is 30 watts times 4.52, or 161 degrees C. The total junction temperature at 25C is 25 plus 160, or 185 C. So the maximum junction temperature for this device happens to be 200 degrees C from the data sheet. However, I think this is very close, and it would be better in terms of reliability if the temperature were lower than 185 degrees C. Probably around 125 to 150 would be much better. But this is a hypothetical case, and this is how you do thermal calculations. Again, you can do this either analytically or empirically with a meter. And again, what I've shown here is all DC values. If you have a transistor or a diode with AC or funny waveforms through it, you have to use the RMS value. And probably the easiest way to do that is to use a RMS meter, multimeter that measures RMS, and put a resistor in series with the device, a low value resistor to measure the current through it, RMS current, and multiply those two, just as we've done here in the DC case. Okay, that's about it. Hope this helps. I'm going to have a few more of these on other different topics similar to this, but this is basically how you run thermal calculations for semiconductors, and hope you find it useful. If so, please like my video and subscribe to it. Thanks very much.